Our last two sets of identities. First, the product of sum. Cosine alpha times cosine beta, right? So this is going to allow us to write product of trig functions, specifically combinations of cosines and sines, as the sum or difference. Cosine alpha times cosine beta is a half the quantity cosine of alpha minus beta plus cosine of alpha plus beta. Then you have sine alpha sine beta, a half the quantity sine of alpha plus beta plus sine of alpha minus beta. Sine of alpha times sine of beta, half the quantity, cosine of alpha minus beta minus cosine of alpha plus beta. Finally, cosine of alpha times sine of beta, half the quantity sine of alpha plus beta minus sine of alpha minus beta. These identities are used in calculus. It feels like they have the heat on here. Yeah. Sum the product. And this will allow us to write the sum of combinations of sines and cosines as a product. Sine alpha plus sine beta, 2 times sine of alpha plus beta over 2 times cosine of alpha minus beta over 2. Sine of alpha minus beta, 2 sine of alpha minus beta over 2 cosine of alpha plus beta over 2. Right, then you have your cosine of alpha minus cosine beta, negative 2 sine alpha plus beta over 2 sine alpha minus beta over 2. Wait a minute. That negative might not be long there. Let me double check. That might be a typo. Nope, okay, that does belong there. And then cosine alpha minus beta, or cosine of alpha plus cosine beta, 2 cosine of alpha plus beta over 2 times cosine of alpha minus beta over 2. Now, these identities, not really that useful. Never really used them. So they're probably just there in theory. Might be some very limited situations where these identities will be useful. As I said, for these, the product sum, you will use these in calculus. These are useful when you're trying to integrate a product of sine and cosine, or a product of sines or a product of cosines. Again, outside of that, they probably have limited uses. So this is very, very short because they don't have a lot of uses. I think the only the only 4 questions are all proofs using the identities. And then we'll move on to solving equations. So let's start with the left-hand side. And let's use the sum the products. You have the sine sum the product and the cosine sum the product. Twice sine of 4a minus 2, not sine, sorry, yeah, sine over 2. And then times cosine of 4a plus 2a over 2. That's the numerator. Denominator, the sum of the product on cosine. Twice sine of 4a plus 2a no. Sorry, I was looking at the wrong one. That should be a plus. That one should be a minus. This should be a cosine. That's right. Cosine minus 2a over 2. And if we look at a few things, you have 2 over 2, right? That's 1. But we also have that cosine term in both the numerator and denominator. That's also 1. What we're left with, sine of 4a plus 2a over 2. That's what? 3a, isn't it? 6a over 2. The sine of 3a over cosine of 3a. Well, what's sine over cosine? That's 10. And so we get our tangent of 3a. Again, we're going to start with the left-hand side. Sine A minus sine B twice sine of A minus B over 2 cosine of A plus B over 2, or I could say those are capital alpha and capital beta. Doesn't matter. Over the sum twice sine A plus B over 2 cosine A minus B over 2. So 2 to 1, that's nice. So let's do this. Look, we have a sine of A minus B over 2 in the numerator, a cosine A minus 2 in the denominator. We also have a cosine of A plus B over 2 in the numerator, and a sine of A plus B over 2 in the denominator. What's sine over cosine? What is cosine over sine? Not quite there yet, though. How else can we write cotangent? Right, it's cosine of sine, or what else? It's 1 over tangent, isn't it? Reciprocal of tangent. Right, secant 1 over cosine, cosecant is 1 over sine, cotangent 1 over tangent. Tangent A minus B over 2 over tangent A plus B over 2 as desired. Let's start by writing cosine cubed as cosine times cosine squared. can switch the order, right? Sine squared times cosine squared, and also factor out that squared. Sine times cosine, though, is a half sine of 2x. Right, double angle for sine. Sine 2x equals 2 sine x. Distribute that square factor. We have a quarter cosine x sine squared of 2x. Use the reduction identity. Sine squared, 1 minus cosine of twice the angle, all over 2. We have 1/8 all times cosine minus cosine of x times cosine of 4x. Yeah, we're getting there. Now use the product to sum for cosine times cosine. Let's actually make these brackets now. Cosine of x times cosine of 4x is a half the quantity cosine x plus 4x minus cosine x minus 4x. Seriously, not at work. Right? But useful property we know about cosine is that it's even. Right? So that means cosine of negative 3x is equal to cosine of positive 3x. Factor out that 1/2. But when you factor a 1/2 out of 1, what are you left with? And again, remember, factoring is the opposite of distributing, right? When you distribute, you multiply. So when you factor, I'm sorry. Yeah, when you distribute, you multiply. So when you factor, you do what? Divide. What's 1 divided by 1/2? 1 divided by 1/2.
1 divided by 1/2.
Yeah. So when you factor 1/2 out of cosine x, you're left with 2 times cosine x. Also, distributing that negative through, right? You'll then have a minus cosine 5x minus cosine 3x, and all that's left to do is to rewrite that because addition is commutative. Why did I use a bracket? I could use a parenthesis. Which is what we wanted. And so, keep in mind with problems like these, you do want to match exactly what they have, right? Which means stopping here is not good enough. You have to write it in the same form, right? So you had to actually switch this order. And this is the last one for the identities. So 1 plus cosine 2x plus cosine 4x plus cosine 6x. Since grouping doesn't matter, let's group it this way first. So we're looking at those two middle cosine terms. Sum the product. I don't need those parentheses. Plus 7 is minus. Twice cosine of the sum of the angles over 2 times cosine the difference of the angles over 2. And we still have that cosine 6x. That's going to be what? First one's 3x, and the second one is negative x. But again, cosine is even. Cosine of negative x and cosine of x are the same. Condition is cumulative and associative. I'm moving cosine of 6x over so I can group the 1 plus cosine of 6x together. We're also going to write this. Cosine of 6x is a double angle, right? It's cosine of 2 times 3x. Now we want to use a double angle identity on cosine. Remember, there are 3 forms. Cosine of 2 theta, cosine squared of theta minus sine squared of theta. Or 1 minus 2 sine squared of theta, right? Or 2 cosine squared of theta minus 1. I'm going to use the 2 cosine squared of theta minus 1. Because you get 1 minus 1 out of that. I'll just wait for PowerPoint to get caught up and finish saving before I move on.
So using the double angle identity, you can use
Out of the 3. Yeah, whichever one fits your needs. Because you can get all of them by using your Pythagorean identity.
I mean, using all of them should be the same, like the same.
That's the same thing, right? If you start with cosine squared minus sine squared, replace cosine squared with 1 minus sine squared from the Pythagorean identity. You'll get the 1 minus 2 sine squared. If instead you replace sine squared with 1 minus cosine squared, you get your 2 cosine squared minus 1. So they're all the same just by using the Pythagorean identity. And so which form you use
Should be
depends on which one's most useful, which one's most advantageous in that specific circumstance.
okay. How do I know which one is the most useful?
Do math for
For 30
20 years, 20, 30 years, and then
and
you'll start to see. Yeah. So unfortunately, it's not an answer that everyone likes, but that's really the only answer. Which one you know is most useful? You just know by doing it. But here, I can give you a tip. You're trying to get to remember 4 cosine x, cosine 2x, cosine 3x. It's only cosines in there, right?
Yeah.
You don't want sine.
Yeah, that would be more work.
So yeah, so that, and what that tells you, well, why don't I just use the 2 cosine squared minus 1 because it doesn't have any sines. It's little things like that you'll start to pick up on.
The details.
Yeah. So for proofs, it's easy because you know what you're going for. But in terms of like if it's an actual evaluation, which one's most useful, you just have to kind of notice. This is going to leave us now with this. I'm also going to, yeah, I'll switch that order as well. 2 cosine squared of 3x plus 2 times, I'm switching the order, cosine x times cosine 3x. And notice we have a cosine, 2 cosine 3x common that we can now factor out. I guess I didn't need to switch that order, but whatever. Leaves us with cosine of 3x plus cosine x, right? Use your sum of product identity. Two cosine 3x times twice cosine of the sum over 2 times cosine of the difference over 2. Two times 2, 4. 3x plus x, 4x over 2 is 2x, right? And then 3x minus x, 2x over 2 is just x. 4 cosine 3x, cosine 2x, cosine x. We just now have to rewrite that. And we have our result. Those are now all of the, I don't know how to word it. Let's put it this way. All of the trig identities that are on a typical trig table. When you're taking calculus, you get like a table in the back of several things. One of the trig identities. These are the ones that are listed all the time. Plus the basic ones that we did. Right, Pythagorean identities, the cofunction properties, even odd, I think sometimes is on there. Writing everything in terms of sines and cosines are on there. Right, so we've covered them all now. Are there any questions on the sum of the product, product to sum? Then we move on to solving equations. This is the last thing we do this semester. There's going to be a slight variation now, though. All the equations we've solved, we've done what? Polynomials, rationals, exponentials, logarithmics. This is now the first time we're dealing with equations that involve periodic functions. Which means with an equation that involves trig, if a solution exists, it's always infinite because it's periodic. So you only have two possibilities. No solution or infinitely many solutions. Which can be a pain. A lot of the time you'll see something like this. It'll say, find all solutions on a given interval. Like 0 to pi. Now, you're not going to have infinitely many. Because you're limiting it to over one full period. 0 to pi. Or I could go 0 to 6 pi, right? More than. But either way, we're limiting it so you no longer have infinitely many solutions. What I'm going to do for this problem is to show you what happens if an interval is not given first. So I'll list out, say list very loosely, the infinitely many solutions. Then we'll go back, we'll look at that interval, and we'll choose from all those infinite solutions which one falls in the interval. Right, and just like when we did the logarithmic and exponential equations, there's no preliminaries really. Best way to learn solving these types of equations is to jump right into it. All the strategies still hold. You want to isolate x. In this case, you want to isolate sine of x. Or you add 1 to both sides first, right? Then you divide by 2. Right now we have sine of x equals a half. Here is where things change. Let's say that was e to the x equals a half. How would you find x? Take the inverse, right? You do the natural log. Likewise, if there was natural log of x equals a half, you take the inverse, right, which is an exponential. X would be e to the 1/2. X squared equals 1/2. Square root both sides, right? Radical is the inverse of a power. Remember, we technically don't have inverse functions for the trig. We were only able to define them by limiting its domain. So you cannot say, let's do this. This does not imply that x is the inverse sine of a half. That's only going to give you one solution. What you have to do is look on the unit circle, possibly. And I think I have cases where it will be on the unit circle as well. Right, but start by looking on the unit circle, you go, okay, where on the unit circle, what angle is sine 1/2? Right? In other words, look on the unit circle, what angle has a terminal point whose sine was what? The x coordinate or the y coordinate? what angle has terminal point on the unit circle with a y coordinate of 1/2? And there's 2 angles on the unit circle. They are pi over 6 and 5 pi over 6. But also, all of their coterminal angles are solutions as well, right? So our solution set is a union of sets. The first is the set of all values, pi over 6 plus a multiple of 2 pi. Right, so pi over 6 plus 2n pi such that n is an integer. Union with the set of all values 5 pi over 6 plus a multiple of 2 pi. That would be the solution if we didn't have an interval. Those are all of the solutions to this equation. Notice what would happen if you just took the inverse sign. Inverse sign of the half is just pi over 6. You would just get pi over 6. You would lose your 5 pi over 6 out of that. Because the range of inverse sign was the right half, right? Minus pi over 2 to positive pi over 2. This is an extremely common mistake when first learning to solve trig equations, is you just take the inverse trig function of both sides and stop. You can't do that. Now, we replace the interval. So of those infinitely many solutions, which solutions are between 0 and 2 pi? I'll call this solution over 0 to 2 pi. Or it's just what? Pi over 6 and 5 pi over 6, isn't it? It's just the 2 that are on the unit circle. So if the question was just simply find all solutions, this would be your answer. Now it's telling us on an interval, so this is the solution. But being able to write out the infinitely many solutions is helpful. Because what if instead of from 0 to 2 pi, I said from 0 to 8 pi? You get pi over 6, 5 pi over 6, but then you find coterminals. So you can get from now 2 pi to 4 pi. So you add 2 pi to each of those solutions. Now from 4 pi to 6 pi, you add 2 pi to those new ones, or 4 pi to the original. And then 6 pi to 8 pi, you have to add 4 pi to the originals. Right? Yeah, 4 pi. No, 6 pi, I'm sorry. 6 pi to the originals. So you have to just keep finding coterminals until you satisfy your interval. And again, I think I'll have examples of that later, either today or Monday, because I'm going to finish this up on Monday. Sine x times cosine x equals 0. Right, now remember your zero property. Take the product of real numbers. If the product of real numbers is 0, then at least one of them must be 0. So we're going to get sine x equals 0 or cosine x equals 0. We'll start with sine x. If sine of x equals 0, and I'm not going to do all infinite solutions, I'm only now considering 0 to 2 pi. So look on the unit circle. What angles have a terminal point with y coordinate 0? Let's bring it up. Not screen. So there's the unit circle for you. Where's the y coordinate 0?
2 pi.
Where else?
Pi.
Where else?
And 0.
2 pi is not an interval. If I go back to the presentation, it's just less than 2 pi. So just 0 pi, right? Those are your two solutions to that one. And then you tackle cosine x equals 0.
Pi over 2. 3 pi over 2.
Pi over 2 or 3 pi over 2. Now you just combine all of them, right? All of those values are solutions. That's your solution set. Use the inverse trig functions here. I just went right to the unit circle. Maybe I should save the inverse trig functions because I'm currently rewriting this course. Maybe we should put those at the end. So I'm not tempted to use them too early. Use the zero property again. right? One of them has to be 0. We're going to have tan x is equal to 1, or sine squared x is equal to 3/4. Right, notice I just did 2 steps at once. I added 3 and divided by 4. This gives you 3 possibilities. Tangent is 1, tangent of x equals 1, or sine of x is equal to negative root 3 over 2, or sine of x is equal to positive root 3 over 2. Right? Because remember, when you take the square root of sine squared, you get absolute value of sine of x. So the absolute value of sine of x is root 3 over 4, which means sine x is either positive or negative of that. Now you go back to your unit circle. So let's, again, just go in order. We'll start with this tangent. Why is that cut off? Oh dear, hold on. Let's fix that. There we go. That should be better. So come on. I'm still doing. Oh, I know why. Hold on. I know why. Because I've adjusted my screen and haven't fixed this. There. Try and make it as centered as possible. That's the only thing I hate about ODS. I can't get it perfectly centered. There we go. Tangent's a little tricky. Because tangent isn't just one coordinate, right? What is tangent in terms of the coordinates? You're right, sine and cosine, but in terms of coordinates, it's what? What was sine?
Y.
What is cosine?
X.
So what's tangent in terms of the coordinates?
Y.
Y over x.
Y over.
So you want to look at your terminal points in the unit circle. Y over x equaling 1 means that both y and x have to be the same, right? Root 2 over 2 and root 2 over 2 are the same. That angle's pi over 4, there's a solution. The other one is where they're both negative root 2 over 2, which is 5 pi over 4. Those are the 2 solutions where tangent x equals 1 over the interval 0 to pi, right? All solutions would be, and all their coterminal points. Or coterminal angles, rather. So those are 2 solutions, pi over 4, 5 pi over 4. Does that make sense how I'm doing that? One is easy. When it's anything but 1, it gets a little bit trickier. Now look at the negative root 3 over 2 for sine. You said what sine is the y coordinate. So what angles has a y coordinate of negative root 3 over 2?
5 pi over 3 and 4 pi over 3.
Yes. I'm going to write them in the other order though. Right, simply because I have to have them in ascending order. It's one of my quirks. And then finally, sine is positive. Root 3 over 2. Why aren't you working? Thank you. So what angles has terminal point with y coordinate of root 3 over 2?
Pi over 3 and pi over 3.
Pi over 3. Solution set. Now remember, with a set, the order in the set doesn't matter, right? Unless it's an ordered set. That's, you're not going to have to worry about that until you take linear algebra. So you can write this in any order you want. Again, I like to keep it in ascending order. So I'll just write it that way. But you can write it any way you want. Well, if you notice, this is quadratic form. Right? Make a change of variable to make it easier. Let W. So just replace sine of x with W. Doesn't that equation then become W squared plus W minus 2 is equal to 0? At this point, what you have is a quadratic equal to 0, right? You know how to solve that. Can that quadratic be factored? So it was W squared plus W minus 2 factor. What is a factor to? W plus 1 times W minus 1, right? From here, we see immediately that we get either W is negative 2 or W is 1, right? I should bring the portable air conditioner with me on Monday. This is just ridiculous. But what was W? Sine of X, right? Where is sine -2? It shouldn't take that long. What's the range of sine? Now I want to write the range of sine and cosine down somewhere, because it's very important. Sine and cosine are only between -1 and +1. So where is sine equal to -2? Nowhere. That is the empty set. That has no solution. Now, where does sine equal 1?
The one coordinate. No.
Which is what? What angle? That gives a single solution of pi/2. So you could write x equals pi/2. I always like to write my solutions as sets. So it's a set of just pi/2. So that I can restart PowerPoint. Finish saving first. We'll divide both sides by cosine squared. No, that didn't fix it. Oh boy, my computer's going to crash soon. this gives us two possibilities, right? Tangent is negative root 3, or tangent is positive root 3. Again, tangent is y over x. This is where I said it's a little tricky, but it's useful if you really know your unit circle. Root 3 over 2 divided by 1/2. Isn't that root 3? Because isn't that the same as just root 3 over 2 times 2? That means we're looking for angles whose terminal point has the coordinates of 1/2 comma root 3 over 2 plus or minus. Because tangent would be either negative root 3 or positive root 3. Again, I'm just going to go one at a time, so look for the negative root 3 first. So you're looking for 1/2 and root 3 over 2, where one of them is negative. And what angles is that?
Like, over 2.
Where am I? What was it?
Like, over 2.
And what else?
4 pi over 2. Oh, wait, can you go back?
Let's see, it will let me. Yeah, there we go.
In that case, 7 pi over 6. Wouldn't they be? No, not right. No, because it's y over x. Okay.
Right, it's y over x, not x over y. Also, for negative root 3, you gave me the wrong angles. You gave me where none were negative and both negative. So I'll just write that down for this one. Because that's for tangent equals positive root 3. Where was it now for negative root 3?
Pi over 6. 5 over 2.
Negative root 3. No, you need one of the coordinates to be negative, but not both.
2 pi over 3.
And where else? Yes. Oh, good. PowerPoint seems to have fixed itself. And again, keep in mind that for all these problems, they are always between 0 and 2 pi. I guess we should mention in here, we wound up dividing by cosine squared, right? Which means cosine can't be 0. So just check that those solutions don't give you cosine equals 0, which they don't. Uh, 2 sine x minus cosecant x equals 1. Well, first, recognize that cosecant's 1 over sine. When solving equations that involve rationals, technically this isn't a rational, right? Rational is a polynomial, but you multiply to get rid of the denominator, right? You clear out denominators. Same idea. So we're going to multiply through by the LCD. Well, in this case, the LCD is easy to see, it's just sine of x. Multiply every term by sine of x to clear up the fraction. We now have quadratic form. And you want to move everything to one side and have it equal to 0. And then if you want to, use a change of variable to make it easier. And 2w squared minus w minus 1 equals 0. Can that be factored? Using only integer coefficients? Can, right? You should see that you get either w is negative 1/2 or w is 1.
What side of it?
Yeah, just waiting for a PowerPoint to get caught up. There we go. There we go. Sine x, negative 1/2, or, what was it, sine x equals 1? We'll start that one first because that's the easiest. That only has a single solution. That only occurs at x equals pi over 2. Now we look at the where sine of x equal to negative 1/2. Right, rectangles has a terminal point with y coordinate of negative 1/2.
Even 5 or 6.
And what else?
7 or 5 or
7
6.
pi over 6. And there's our solution set. When in doubt, write everything in terms of sine and cosine. Secant 1 over cosine. Cosine is sine over cosine. And cotangent is cosine over sine. Common denominator is cosine times sine, right? So that's what you multiply everything by. We'll get 2 sine of x equals sine squared plus cosine squared, right? What's sine squared plus cosine squared?
We multiply cosine and sine, right?
You multiply, yeah, you're multiplying everything by a sine times cosine. That means that 2 sine of x is 1. Sine of x is a half, right? Where is the y coordinate 1/2?
Pi over 6 and pi over 6.
And there's our solution set. Tan x plus 3 cotangent is equal to 4. Well, let's recognize cotangent as 1 over tangent. Then multiply through by tangent, right? Then once we rearrange, get everything on the one side, tangent squared of x minus 4 tangent of x plus 3 equals 0. Let's let it go and use this time. I'm sick of using W. T. Replace tangent of x with t. Does that factor? Remember for factoring. And again, we want to factor in terms of integer coefficients. Factors of 3, when added, give 4. Now, 3 only has 2 factors, right? What are the factors of 3? So factors of 3. Now what are factors?
Could be 9.
9's a multiple.
Oh,
Factors of 3 are 1 and 3. Right, factors are something when you multiply, you give you 3. Right, so you always have pairs of factors. 1 times 3, 3. 9 would have 3 factors. Yeah, 2 pairs. 1 and 9, 3 and 3. 1 plus 3 is 4, so this can be factored. Why did I write 4? T minus 3, T minus 1. T is either 3 or 1. That means tangent is either 3 or 1. Start with 1. We already solved that. Let's just bring up the unit circle. Remember, tangent y over x. So for tangent to be 1, your x and y coordinates have to be the same. What angles have the x coordinate and y coordinate being identical? And
5.
now tangent equals 3. Again, you have to keep in mind tangent's y over x. So you're looking for a point where the y coordinate divided by the x coordinate gives you 3. And there are no points. That doesn't mean the solution doesn't exist. Remember, tangent can be all real numbers. It's just not an angle that's located on the unit circle. So here's what we're going to have to do. Yeah, I would have to do the inverse trig functions first. X has to be the inverse tangent of 3. What was the range of inverse tangent?
Minus 5 or 5.
Inverse tangent of 3 is going to give you an angle in which quadrant? 4 or 1?
Why not?
You said fourth?
Yeah.
First. Where's tangent positive? Tangent's negative in the fourth quadrant, right? Because you have a negative y coordinate and positive x. Whereas in the first, they're both positive. And so because, remember, inverse tangent of 3 is the same thing as saying tangent equals 3. So where's tangent positive? Quadrant 1. So I'm going to draw this out real quick. I'm going to call it theta. No, I'm going to call it x, because that's what it's listed as x. That would be our x. But we also know that tangent is positive in quadrant 3, right? Well, if you look, that angle there is also x. But that's not what we want. We want it to be between 0 and 2 pi. X is between 0 and pi over 2. We want that angle. What is that angle? Well, we know what that angle is, right? Which is what in radians? Just pi, right? Pi, oh, and then don't we go down x? That's pi plus x. Oh, but x is inverse tangent of 3. There's your second solution. You multiply by tangent, so we just have to make sure that tangent isn't 0, which at none of those angles is tangent 0. So here's our solution set. Pi over 4, inverse tangent of 3, 5 pi over 4, and then inverse tangent of 3 plus pi. Right, so in scenarios like that, where you're not going to be able to get a nice angle, right, i.e. an angle that's not on the unit circle, you could try and use identities if possible, like some difference identities like we did for like pi over 12. Pi over 12 is not an angle on the unit circle, which I recommend you do if possible. Here it's not possible, so you have to then use the inverse trig functions, but you have to think. Right. If that was -3 instead, you'd be down here, right? But that's not even an angle between 0 and 2 pi. Right, that's 0 to minus pi over 2. Or pi over 2 to 0, minus pi over 2 to 0 rather, because of the way that the range works. You have to do that angle plus 2 pi. That's just for the quadrant 4 angle. Then you have to try to figure out, okay, now what's my quadrant 2 angle? In terms of the inverse tangent of -3. And I think that is that. It'd be pi minus that angle, because that angle is negative. So it'd be pi minus the inverse tangent of -3 as your second solution. And that's what starts to make these equations a bit tricky. And so really up until there, right, so up through question 7 of equations are pretty straightforward. Not much going on. Question 8 is the first one where we start not. Most of the equations after this are also going to have knots in them. Right, so no more straightforwardness. However, those will have to wait until Monday. Any questions on the equations so far? So, like I said, question 9, that we're going to start Monday. We're going to start there on Monday. Yes, okay. So I didn't write this in there, but let's do it now, and don't leave just yet. Let me double check. I'm pretty sure it's 10:15. Yes, 10:15. So the third exam, next Wednesday, the 7th at 10:15. The exam is comprehensive. However, what I did was I broke the exam into 2 parts. So the exam is out of 100 points total. Part 1 is 70 points, which is only material since exam 2. Then part 2 is 30 points, and that'll be material from the first 2 exams. So the heaviest focus is on the new stuff. So 70% of the exam is new. 30% is the old stuff. So keep that in mind when writing up your reference sheet. And I think I kept it where it was 15 points from exam 1, 15 points from exam 2. I tried to do that. I may not have gotten that exactly, but I tried to split it up evenly. But there's definitely 70 points on exam on new stuff. So keep that in mind. Monday we'll finish up equations. The last 2 homeworks are also due on the 7th before the exam. And that's on the sum, the product sum, and the equations. Have a good weekend.